Now, the right-angle altitudes theorem has a couple of corollaries that come along with it. Now that we know the definition of geometric mean, these corollaries should be fairly easy to understand. This first corollary is called the hypotenuse corollary to the right triangle altitude theorem. The length of the altitude of the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. The words alone seem a bit confusing, but when we see a picture, it looks more like this. If ABC is a right triangle, and it is, we can see that B there is a right angle, and segment BD is the altitude to the hypotenuse, then AD, this segment, this part of the hypotenuse, over the altitude, is equal to the length of the altitude over DC, the other portion of the hypotenuse. Notice that both the means in this proportion are BD, so BD is the geometric mean of AD and CD. Our second corollary is the leg corollary to the right triangle altitude theorem. You can see all of these words over here. It's long. The altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Oh my word, I said that in one breath. Let's look and see what it means using a figure. If triangle ABC is a right triangle, and segment BD is the altitude to the hypotenuse, then the length of AC, the entire hypotenuse, over AB, the leg on the left, is equal to AB over AD, which is the segment that is the left-hand side of the hypotenuse there. That means segment AB is going to be the geometric mean of the whole hypotenuse AC and the segment adjacent or closest to segment AB. And likewise, AC over CB is equal to CB over CD. So segment BC is the geometric mean of segment AC and segment DC. So in summary, I'm kind of hoping this kind of helps out. Ooh, I don't know if it does or not. But the hypotenuse corollary allows us to say that the altitude to the hypotenuse is the geometric mean of the two segments of the hypotenuse that it creates. So the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. The leg corollary actually allows us to do two proportions. It says that each corresponding leg, so here this first one we're talking about L1, is the geometric mean of the entire hypotenuse and the segment of the hypotenuse adjacent to the leg. So the first leg is the geometric mean of the hypotenuse and the shorter segment of the hypotenuse. So the short leg, shorter segment. And if we look at the other leg here, the longer leg is going to be the geometric mean of the entire hypotenuse and the longer portion of the hypotenuse, which will be adjacent to the longer leg. Again, I don't know if that helps, but having this in your notes might help you set up your proportions until you get used to them. So now let's combine all of these things into a single problem. Yay! You knew we were going to do that, right? So let's take a look here. We have x is the altitude of a right triangle to the hypotenuse. So that means that x has to be the geometric mean of 8 and 10. The cross products property tells us that x squared is going to equal 80. Oh, of course it's not going to be nice, because when we take the square root of both sides of this equation, the square root of x squared is just x, but 80, we need two numbers that multiply to equal 80. Well, there's 1 and 80, but that doesn't help much. I'm not even going to look at 2 because it's not a perfect square. 4 goes into 80 20 times. Not going to look at 5 because it's not a perfect square. 6 isn't, 7 isn't, 8 isn't. 9 doesn't go into 80 at all. There's 10 times 8, but neither one of those is a perfect square. 12 doesn't go into it. Neither does 11, 13, 14, 15 doesn't go. 16 goes into it. 5. Oh, I should have looked at 5. Duh! Square root of 16 times the square root of 5 is equal to the square root of 80. And of course we can take the square root of 16, which is 4. And we can't take the square root of 5, so we just tack it on to the end there. X is going to be 4 times the square root of 5. Now let's attack y. Y is going to be the geometric mean of the portion of the hypotenuse that's closest to it, so 8, and the entire hypotenuse. 8 plus 10 is 18. So y squared is going to equal 18 times 8 is, 144. Why did I say whoa, you ask? Because when we take the square root of both sides of the equation, the square root of y squared is y, and the square root of 144 happens to be 12. So that's a nice, neat number there. Any questions? If so, please write them in your notes and ask them in class.